In this video, we'll review how to solve trigonometric equations, that is, equations with sine, cosine, or tangent. Keep in mind when solving for angles of rotation, theta, there are often two angles between 0 and 2 pi that will have the same sine or cosine values. Now sine is a measure of y over r. The y's are positive in two quadrants, quadrants 1 and 2. So sine is positive in quadrants 1 and 2. Now the y values are negative in quadrants 3 and 4, so sine is negative in quadrants 3 and 4. Cosine is a measure of x over r. X's are positive in quadrants 1 and 4, so cosine is positive in quadrants 1 and 4. Cosine will be negative in quadrants 2 and 3 because that's where x's are negative. Now tangent's a ratio of y over x. Therefore tangent will be positive whenever y and x have the same signs. So tangent will be positive in quadrants 1 and 3 because in quadrant 1, x and y are both positive, and quadrant 3, x and y are both negative. Tangent's going to be negative when x and y have different signs. That means tangent's going to be negative in quadrants 2 and 4. It's negative in quadrant 2 because x is negative, but y is positive. And it's negative in quadrant 4 because now y is negative, but x is positive. Anytime only one of them is negative, the tangent's negative. Now let's put this to use. We're going to go ahead and solve these three trig equations, and we're going to keep all the solutions between 0 and 2 pi. The first one's already pretty much solved out. The sine of theta is by itself, and it equals negative root 3 over 2. We just need to figure out where sine, or y's, are negative root 3 over 2. From our unit circle, I know that y's are negative in two places, and it's going to be negative root 3 over 2 at either 5 pi over 3 in quadrant 4, or 4 pi over 3 in quadrant 3. This is because those coordinates, negative 1/2, comma negative root 3 over 2, and positive 1/2, comma negative root 3 over 2, both have y values that are negative root 3 over 2's. So both 4 pi over 3 and 5 pi over 3 are solutions to the equation. Now the other two equations are going to take a little bit more work. We're going to have to get the sines and the cosines by themselves. Alright, for problem number 2, we're going to start by subtracting 1 from both sides. This gives us 2 cosine theta is 1. We'll then divide both sides by 2, and we get cosine theta is 1/2. Now cosine is a measure of the x's. X is positive in two places. X can be positive in quadrant 1, and it can be positive in quadrant 4. Now I know that 1/2 is one of the values that's common on the unit circle. X is 1/2 at pi over 3, and x is also 1/2 at 5 pi over 3. So both pi over 3 and 5 pi over 3 are going to be solutions to the equation 2 cosine theta plus 1 equals 2. Now the next problem's a little trickier. Here I see we have sine squared. In order to undo that square, we're going to have to square root the equation at some point. So when we do this, keep in mind that when we have a square that we have to square root, we tend to pick up twice as many solutions. You'll see in a minute what I mean by that. Alright, we're going to begin by adding 1 to both sides, and we get 4 sine squared theta is 3. We'll then divide both sides by 4, and we get sine squared theta equals 3/4. The way we're going to undo the squaring now is to square root both sides. It's inverse operation. However, when you square root a square, you're going to get plus or minus solutions on the other side. That means the sine of theta is going to be plus or minus root 3 over root 4. Now 4 is a perfect square down there on the bottom. So we're going to get sine theta equals plus or minus root 3 over just 2. The square root of 4 is 2. Now this is the value that's on the unit circle, and sine is going to be positive in two places. The y's would be root 3 over 2 positive in quadrants 1 and 2, and that would be at pi over 3 and 2 pi over 3. But sine theta can also be negative root 3 over 2, which also happens in two places. It'll happen at 4 pi over 3 and 5 pi over 3. At these four angles, we have a y value that is either a positive or a negative root 3 over 2. So all four solutions are going to be possible between 0 and 2 pi. So therefore theta equals pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Now here's two more problems. Why don't you go ahead and work these two problems out, pause the video, and then resume it when you're ready to check your answers. I'll give you a moment. Alright, hopefully you've had a chance to work these problems. We're going to start number 4 by subtracting 3 from both sides, and we get 5 cosine theta is 0. Dividing both sides by 5, we get cosine theta is still 0. And I know that there's two places where the x or cosine can be 0, straight up and straight down on the unit circle. So we can say that theta is either pi over 2, because x is 0 when it's 0, 1, Or it could be 3 pi over 2, because x is still 0, when it's 0 now, negative 1. So both pi over 2 and 3 pi over 2 are solutions to the equation. Now in number 5, hopefully you caught that it's cosine squared. The squared means we tend to pick up twice as many solutions, so this one probably has 4 solutions. Alright, to begin, we're going to subtract 5 from both sides, and we get 2 cosine squared theta equals 1. We'll then divide both sides by 2, and we get cosine squared theta is 1/2. Square rooting both sides, we get cosine theta is plus or minus root 1 over root 2. Now the square root of 1 is just going to be 1. So we get cosine of theta is plus or minus 1 over root 2. Now we don't want to leave it like this. We don't leave a radical on the bottom, so we're going to do what's called rationalizing the denominator. The way we're going to get that radical off the bottom is we're going to multiply top and bottom of the fraction by root 2. 1 times root 2 in the numerator is going to be root 2, and root 2 times root 2 in the denominator is going to be the square root of 4, which is just 2. Therefore, when we rationalize the denominator, we get cosine theta is plus or minus root 2 over 2. Alright, when we go to solve now, drawing the picture, I know that cosine can be positive root 2 over 2 in 2 places, in quadrants 1 and 4. And those solutions would be pi over 4 and 7 pi over 4. But cosine theta can also be negative root 2 over 2 in 2 more places. It can be at 3 pi over 4 and 5 pi over 4. All of these have x values that are either a positive or a negative root 2 over 2. So all 4 solutions are going to be solutions to this equation. Therefore, theta could be pi over 4, 3 pi over 4, 5 pi over 4, or 7 pi over 4. Now, we're not always going to get answers that are going to be on the unit circle. And in order to avoid confusion when solving for these non-common angles outside of quadrant 1, we're instead going to solve for the reference angle, which we call theta prime, and then use theta prime to find the actual theta. Now keep in mind the reference angle is a positive acute angle that takes us from the terminal side of our angle to the nearest x-axis. Keep in mind the reference angle is positive, acute, and always to the nearest x-axis, never the y-axis. If this is theta, then theta prime would be the piece that takes us to the nearest x-axis. So if we're in quadrant 2, it's the little piece below the terminal side of the angle that takes us to the nearest x-axis. If we're in quadrant 3, we're past 180 or past pi, so it's the piece that takes us back from the terminal side to the x-axis. That would be theta prime here. If we're in quadrant 4, we're a little short of 360 or 2 pi, so it's the piece that takes us from a terminal side to the x-axis where 2 pi or 360 is. Now the way we're going to use this to actually find the angle of revolution is based on whether we're looking for it in degrees or radians. So if it's in degrees, keep in mind that in quadrant 1, theta would be theta prime because the angle is already acute and positive. If you're in quadrant 2, you're a little short of 180. Therefore, theta is 180 minus whatever that reference angle theta prime is. In quadrant 3, you're a little bit more than 180. So theta is 180 plus theta prime. And in quadrant 4, you're short of 360. The amount you're short is theta prime. So here, in quadrant 4, theta equals 360 minus theta prime. Now we can do these in radians also. We're just going to substitute 180 degrees for pi and 360 for 2 pi. So in quadrant 1, theta is theta prime. In quadrant 2, you're short of pi. In quadrant 3, you're a little bit more than pi. In quadrant 4, you're short of 2 pi. So let's look at how to use these on some actual equations now. In problem number 6, we're going to solve between 0 and 2 pi. And it's not going to be one of our common angles, so we're going to need a calculator on this. So to begin, we start by subtracting 3 from both sides. We want to get the cosine theta by itself. We want to isolate it. So if we subtract 3 from both sides, we get 4 cosine theta equals 1. We'll then divide both sides by 4 and get cosine theta is 1/4. Now that 1/4 value is something that does not exist on the unit circle. So I'm going to need to use my calculator and make sure it's set to radians. I know I want to use radians because my restriction says between 0 and 2 pi. So put my mode in radians. I'll then find theta prime by typing inverse cosine 1/4 and pressing enter. And it tells me that theta prime is going to be about 1.31 radians. Now this reference angle, I'm going to now use it to find my actual angles of revolution. Now I said that cosine can be positive in 2 places, quadrants 1 and 4. If we're in quadrant 1, then theta is theta prime in that quadrant. So the 1.31 radians is one of the solutions. Now the other solution is in quadrant 4. In quadrant 4, we're short of 2 pi. And the amount we're short is that theta prime, or in this case 1.31 radians. So for the other solution, we're going to say that theta is 2 pi minus 1.31 radians. So taking our calculator, typing in 2 pi minus, and instead of doing 1.31, I'll just recall the answer to be a little bit more exact, and I'll find out it's about 4.97 radians. So both theta is at 1.31 radians and 4.97 radians. Both are solutions to this equation. For problem number 7, the restriction says between 0 and 360. That means I need to change my calculator now to degrees. So I'll push mode, degrees, and solve this one now. We'll start by subtracting 5 from both sides. We'll then divide both sides by 7, and we get sine theta is negative 3/7. Now there's two places where the y is going to be negative. But to begin with, I'm going to find theta prime. Theta prime is going to be the inverse sine, and I'm going to drop the negative. The reason I drop the negative is to guarantee that the reference angle theta prime is both acute and positive. Using my calculator, making sure it's in degrees mode, inverse sine 3/7, pushing enter, I see that theta prime is about 25.38 degrees. Now this doesn't mean that theta is 25.30 degrees. It means that the reference angle is. Sine is negative in 2 places, that is quadrants 3 and 4. In quadrant 3, you're more than 180. The amount you're going to be more than 180 is our theta prime, 25.38 degrees. So to find the first solution, we're going to say that theta is 180 plus 25.38 degrees, or in quadrant 4, we're going to be short of 360, which means we're 360 minus the 25.38 degrees. Using our calculator, I'll now find both solutions. 180 plus 25.38 is going to give me a solution of 205.38 degrees, and then 360 minus the 25.38 degrees is about 334.62 degrees. Both of these are solutions to the equation. Now let's look at tangent. I've got two other problems, and these are tangents. Tangent is a ratio of y over x. So when we do this, it's a little bit trickier because we've got to figure out what the y to x ratio would be. All right, here we go. We're going to start it like we had other problems. We're going to start by subtracting 1 from both sides. We want to get tangent by itself. So I get 5 tangent theta is 5, and then divide both sides by 5. Tangent theta is 1. This means that y over x is 1. The only way that you can divide two numbers and get a quotient of 1 is when both the numerator and denominator are equal. That means the y and x values are equal. Now tangent's positive in 2 places, quadrants 1 and 3. Now I need to be in quadrants 1 and 3, and I need x and y to be equal. That means it's got to be at some interval of pi over 4s. At pi over 4s, the x and y values are equal. So in quadrant 1, it's going to be pi over 4, and in quadrant 3, it's going to be 5 pi over 4. Notice that both coordinates have x and y values that are equal. Root 2 over 2 divided by root 2 over 2 will be 1. And the same when they're both negatives. So our solutions are going to be pi over 4 and 5 pi over 4. For number 9 here, it's almost solved out. The only thing we got to do is divide by negative 6 and then simplify it. We get tangent theta is 2 root 3 over negative 6, and we can simplify that 2 over negative 6. That's going to give me 1 over negative 3, or tangent theta is root 3 over negative 3. Now keeping in mind tangent's y over x. This means that the y value up top is smaller because root 3 is smaller than 3, so the y is the smaller piece, the x is the larger piece. Now tangent's negative in 2 places. It's negative in quadrants 2 and 4. I just need to figure out what points to use. Now I'm thinking of my unit circle, and I know that at the pi over 6's, the y's are smaller than the x's because you're more over than you are up. Sorry, you're more over than you are up. So, and to solve this, I'm going to use 5 pi over 6 and then also 11 pi over 6. Again, this is true because if we look at the coordinates, the y value 1/2 is smaller than the x value root 3 over 2's. So both 5 pi over 6 and 11 pi over 6 are solutions to this tangent problem. Keep in mind, when y is smaller, you're more over than you are up. When x is smaller, then you're more up than you are over. All right, thank you for watching this video, and hopefully it helps you understand how to solve trigonometric equations.